Okay, let me start with lecture number 2 with this lecture slide. This lecture slide, one extra lecture slide, I prepared for the introduction of this course or this class. And actually the videos, all the videos are taken during the class in Gyeongbuk National University here. So I did some minor editing or some minor changes to that videos. And I inserted one lecture slide to review the content of previous lecture and introduce some conceptual idea of upcoming class. So I present lecture number 2, okay, after finishing this. So this part is summary of previous lecture, lecture number 1. So we discussed several things during the last lecture, and the two most important concepts I'd like to emphasize is this one. The first one is the concept of averaging adapted to 3 basic converters. So here we have input voltage. This is our voltage load resistor, filter capacitor. In between we have this one stability switch and inductor. So this is the A terminal where active switch is connected, and this is the P terminal where passive switch is connected, and the C refers to the common terminal connected to the inductor, and this ILT is inductor current. So with this position, assume this is connected to here, to here, to here, then it becomes the buck converter. If you rotate this 3-terminal switching device by 120 degree, that becomes boost converter, and additional rotation, that becomes buck boost converter. So this could represent any of 3 basic converters and all the PWM converters. And this illustrates the concept of the averaging of inductor current, ILT, and this is on time period, this is off time period. During this on-time period DTS, this inductor current will evolve based on the circuit equation of on-time circuit. So it will go like this, and at this moment, it starts decaying some nonlinear fashion like this. Okay, and after this is the off-time period. It goes up, goes down, goes up, goes down, and gradually increase. Okay. And eventually it will trace out this triangular type nonlinear curve. Okay. And the circuit averaging or this power stage averaging means somehow we want to develop a circuit model that trace out, that generate this waveform time average version of this triangular shape nonlinear curve. So this red one is response of average model, and the inductor current of average model tracks the time average version of ILT. This ILT bar is time average version of this purple waveforms. This bar indicate the averaging variable, circuit variable under the bar here. Okay. So this is the concept of average inductor current. So we discussed that this Vs and the capacitor and this resistor and this inductor, they remain invariant during this averaging process, meaning they stay their original position with their circuit values, circuit parameter values. So we don't have to worry about this linear time invariant component, and we only concerned with this active switch and passive switch. Okay, so we take out them and we draw the active switch here and the passive switch here, and we named them as PWM switch. Okay, this is the notation or the circuit diagram of PWM switch, which is SPDT switch. This is A terminal, P terminal, common terminal, and this is the switch drive signal. And during this time period, switch is turned on and this diode is automatically turned off. And during this off time, this switch is turned off. Then the diode is turned on automatically to form the freewheeling path. Okay. This is the operation of the PWM switch. We named this as the 3-terminal switch and operating on the principle of PWM. And this is the notation, symbolic notation of PWM switch. So we have A, P, C terminals, and the VAP and the IC is here. And they are continuous variable. So I'll explain that later. This is a continuous variable, and this IC is continuous variable. It must be continuous variable because C is connected to the inductor. So inductor current should be continuous all the time. So this is a continuous variable here. Okay. When switch is connected to A, then VCP is simply same as VAP. When this is connected to this P terminal, VCP becomes 0. When this switch is connected to this A terminal, IA is simply IC. When this is connected to P terminal, IA becomes 0. So these two variables are continuous variable, and these two red variables are discontinuous variable. This is called PWM switch. Okay. So we discussed these two things and the other things in the last class, and this class, title of this class is average model of PWM switch and continuous duty ratio. Purpose of this is if we develop average model of this or this, which is the same thing, then we derive the average model of entire power stage because they remain invariant. So by combining average value of this and the remaining part of this power stage, we can obtain the average model of entire power stage. Okay. So in this lecture number 2, we'll discuss this, and this is the summary of the output of this lecture number 2. Okay. So first, this is the switch equation of the PWM switch. So the functional description of this is transferred this equation form, which has a form of equation. So VCP is same as VAP when this is connected to A, okay, and it becomes 0 when this is connected to P. So this QT can be 1 or 0 depending on the time period. For on time period, DTS QT is 1. That means switch is connected to A. Then VCP is same as VP. Otherwise, VCP is 0. Okay. VAP is fixed value all the time. And here, when switch is connected to A during this time period, QT becomes 1. That means IA is same as IC. Otherwise, this IA is 0 because QT is 0. Okay. So this has the form of equation, but actually it simply describes the functional behavior of this PWM switch. But this is very important because it has the form of the equation. Then we can perform average operation on this equation to obtain the average model of this switch, which describes the average circuit waveforms of PWM switch. Okay, so this is the result of this lecture. Okay, in this lecture, which follows after this slide, will details the every steps about this. This is a conclusion of that result, that analysis. So this is the equation of average circuit variable associated with this PWM switch. So VAP bar, which is average version of VAP, is simply, this is VCP, okay? VCP bar is simply the DT times average version of VAP. So this equation is the same as this. we just put bar sign here, and the QT is replaced with DT. Okay, I'll explain the implication of the DT shortly. Okay, and IA bar is DT times IC bar. This indicates that average value of IA is same as average value of IC times DT. Okay, so this DT is a continuous variable in here. So some of this the continuous variable, and this is a discontinuous variable, and this is some switching variables. So it's called the switch signal. So it has the value of 1 or 0. So apparently this continuous variable, but in here everything is a continuous variable. Okay, so we replace the QT with DT. So DT is defined like this, right? So implication of this equation is we integrate the value of the QT, which is 1 or 0, for the switching period, and divide that by the switching period. Okay, so this is called the moving average, and this average, the evaluation period of averaging is TS, switching period. Okay, that means let's consider these waveforms. This is actual switch drive signal QT, and this assume the duty ratio of this is 0.5. So during half the switching period, this value is 1, and the remaining half the value becomes 0. So we integrate this value for this period and divide this by that TS period. Then this value becomes 0.5, and we slide this evaluation window by this much. Then still this is 0.5 because we are losing this much. We are losing this much. Oh, sorry. Here we are losing, let me use this, we are losing this much, but we are gaining this much, same area. So this duty ratio remains the same, and this value is 0.5. Okay, same is true for this period and this period. So if this is the periodic, then this DT is constant. Okay, time invariant variable, but in general, this period will be changed. On time period will be varied. Then this becomes some continuous variable. So it's called the continuous duty ratio, DT. Okay. So the equation is obvious. Maybe we should have some assumption called small signal assumption. Details about that assumption will be presented in the next slide. Okay. And this is the equation. This equation is very familiar to us. This equation is the same as equation of this ideal transformer. So this is ideal transformer. VAP is here, VAP bar is here, then VCP bar is this times this duty ratio, IC bar is here, then IA bar is this times this DT. That is the equation of ideal transformer. So average model of PWM equation is represented by this ideal transformer, but we are not saying this ideal transformer is the same as average model of PWM switch. We are not saying that, but equation is the same. Okay, so functional description of them are the same, but in here, distance ratio DT is a time varying variable. In ideal transformer, this must be a constant. But here, this distance ratio is 1 to duty ratio of this converter, which is time varying variable. Another difference between ideal transformer and this average model of the PWM switch is ideal switch is a two-terminal device, which has this 4 port, but in here, this port and this port, they are initially connected. So this is a 3-terminal non-linear device, which has a form of equation form of the ideal transformer. That is called average model of PWM switch. Okay, and this continuous duty ratio is used as the turns ratio in this ideal transformer representation. Okay, in the next slide, we'll discuss the entire details about this. Okay, again, I minorly edited this video after finishing the lecture. After finishing the semester, there are some interruptions and some unnatural connections, some digressions, and something. Okay, so please understand that this video is some minorly edited version of live class video. Okay, all right. So we'll go with the next slide regarding this. Slide shows the concept of PWM switch. You have buck converter, boost converter, buck boost converter. They have common structure, which is this one. This is called SPDT switch, and we renamed it PWM switch. Okay, so PWM switch is here. So this is borderline. So I'm talking about this. Somehow this slide is busy. Okay. Usually I don't like the busy slide. I'm trying to make everything simple. Only the key idea will be here, but somehow it was not easy to split into two lecture slides, so I combined everything. Okay, so this is a circuit equation which can be applied commonly all these three converters. So we have continuous variable, which is voltage across this AP, voltage across this AP as a continuous variable. Okay, actually there is the voltage, constant voltage, and this common terminal C is carrying inductor current all the time. So this is a continuous variable, and this is a continuous variable, and the other variable, for example, voltage across here or current through this A is this continuous variable. First, the continuous variable VAP is, it is VS for the buck converter, and this one is minus VO for boost converter, and for buck boost converter, there is VS plus VO. They're shown here, and IL is the same as IC for this converter and for this converter, but the boost converter, this IL and IC is opposite because IC is defined as current leaving from this common terminal. Okay, so this is the direction of the IC, and this is opposite to the IL. So we have minus sign here. Okay, so this is the symbol of PWM switch. This is the symbol, right? So when switch is connected to A, this VS becomes VCP, something like that. Okay, so we already went through this, so I don't repeat that. So, but this is the discontinuous variable VCP, voltage across this CP is discontinuous variable, and this voltage is same as this one when switch is connected to the A throw. Okay, and it becomes a 0 when this pole is connected to this P throw. So this is the discontinuous variable, and the same is true for the IA. When this is connected here, IA is the same as IC, and when this is connected here, IA becomes 0. Okay, so there is a rule, and this is just the symbol of PWM switch, and this is the equation of PWM switch. So this is continuous circuit variables, and this is discontinuous circuit variables. So we load this equation in this fashion because with this and this equation along with this definition of the switching function completely describe the circuit structure or voltage current relationship of this PWM switch. Okay, so this is very good. Okay, very nice representation of this, but this does not mean much. It just explains the operation of this, but why with this, but with nonetheless with this, we can have the, we can average the all the waveforms. Okay, with this equation, this is the discontinuous equation, discontinuous variable, but we can average them using this expression as shown in this lecture slide. Okay. So this is the average equation of PWM switch. This is the average equation. This is the description of PWM switch. Just numerical, the equational description of operation of SPDT switch. It's not the equation. It requires definition of the QT. But still, you can average this. So we put bar here. So VCP average in time is average of these two things combined. We first multiply this and we take the average of this. Okay. Then maybe you want to separate this bar, long bar, in the middle. But that is not allowed. It's different from the averaging operation. It's not working that way. So we need some approximation. This VAP is replaced with this VAP bar, which is constant. Okay. Then this constant comes in front. So it comes in front. Okay. This is a constant. Because of that, this guy is coming out of this bar side. Then we have this. Okay. This is the digital signal. QT is digital signal 1 and 0. Then somehow we have definition of this. This is the what? Definition of continuous duty ratio. With this will be transformed to the continuous waveforms. Then this one is okay. Okay. So this is complete in mathematical sense. With the assumption, this one, small signal assumption means the VAP, this is 0, and this dotted line is actual VF, instantaneous curve of VF, okay, and this is the average value of this, and this small signal assumption is the deviation of this from this average value is sufficiently small. Whenever we say something is sufficiently small, for example, this one, this IC, you have IC is combination of DC component, IC, large I, large C, and this small IC hat, which is AC waveform, in particular sinusoidal disturbance, and the magnitude of this is much small. Magnitude of this AC signal is much smaller than DC value of this signal. Something like this is called the small signal assumption. So small signal assumption is all around us when we are dealing with this PWM converter. Without that assumption, it is impossible to move forward. Okay. So with this, everything is possible. So with this assumption, so we have this because this is continuous duty ratio, and the next slide will show some exact definition of this. Okay, so let's take this granted, assume this is correct, then we have this. This is not a PWM switch. This is the symbol, just the symbol of PWM switch. You are using this symbol. This is just the symbol of PWM switch, and this is average equation of PWM switch or average model of PWM switch. So this one is okay, all right? But this equation is familiar to us because we have the device called ideal transformer. It satisfies the current and voltage equation of ideal transformer. I'm sorry. 나중에 전화할게. 수업 중. My old friend, best friend, he was a professor in Hanyang University. He retired 2 years ago. We are in same high school and university. He's a good guy. And this is the average equation of PWM switch, and this is converted to this circuit model using the definition of ideal transformer. So ideal transformer in here, this VCP is VAP times DT. So we assume this is the turns ratio notation in ideal transformer, and IA is IC times DT. Okay, so this is a continuous variable, and it contains the DC and the AC component all together because this is the average value. Okay, so it contains DC and AC, and this, as I said in the last lecture, this terminal and this terminal are connected together. So this is a 3-terminal nonlinear switching device. It is called PWM switch. It's the same as the SPDT switch, but it has different meaning, and it got this mathematical description using the switching function and this continuous duty ratio. So this is equation, this is not an equation, some explanation. And you put bar everywhere, and you replace QT with DT, then that becomes circuit equation of continuous waveform relations of PWM switch. Okay, so you skip all of these steps and just put bar everywhere and replace this with DT, then you will get the average model of PWM switch. Okay, so this explains some details about the definition of continuous duty ratio DT, and this is the signal comparability. Comparable means they can match, they can use it all together as comparable and comparability. Previously I spelled wrong. Okay, so this is the correct spelling, comparability. Because of comparability problem, some of waveforms, some average waveforms are continuous variable, but this DT is QT is non-continuous variable. So to have this, to match the comparability between the signals, we derived this DT from QT. Okay, this is the graphical demonstration of mathematical operation of this. Okay, let me explain this one more time. So this is actual switching function. It's the conceptual things. When switch is closed, it is 1. When switch open, it is 0. So this is a digital signal, and this is the actual duty ratio. So duty ratio during this period is 1/3, 1/3, 1/3, 2/3, 2/3, 1/3, 1/3, something like that. But this is the discrete, discontinuous waveforms. So we need to convert that into continuous waveforms, continuous time waveforms. So we perform this. Okay, so this operation is shown here. Okay, so period integration is t minus ts, and the upper bound is t. Okay, you can use here t, just t, and we can use here t plus ts, but we are using this. That means you are looking back when evaluating the duty ratio. So we wait until this time, and at this point we determine the duty ratio of this signal during this switching period. Okay, so this notation is important, so you should realize this. So with this, you are looking back, not forward. Looking back. Okay, so for this is the actual duty ratio, all right, and we evaluate continuous duty ratio here and here. Okay, so for example, this is the periodic. Assume this is the periodic. We don't have to assume this. This is periodic. Then you move this. This is the window of the integration period. Okay, we are sliding this entirely. We start from here, then we reached here. You are looking back at this point, then this duty ratio is also 1/3. Okay, so let's consider these 3 cases: case 1, case 2, case 3. Okay. For case 1, you are looking back the duty ratio of previous switching cycle, which is 1/3. Here, still this is 1/3. Okay, because of this, at this point it is 1/3. But at this point, you are looking back. At this point to this direction, then duty ratio is 2/3. So 2/3 is here. Okay. In the middle, suppose this. Okay. Then this value is some number in between 1/3 and 2/3. Okay. So we have this slope ramp in between this value and this value. Same is true here. So we have 3 different signals associated with PWM waveforms. So this is the switching function, actual duty ratio. This is a continuous duty ratio. So this is a continuous waveforms. Okay. So there is a, this is a continuous. Everything is continuous. So we will be using this. All right. So obviously, when this one is this duty ratio is evaluated at this point, always we are looking back. Then this is duty ratio evaluated at KTC is dk is the actual duty ratio at case period. If this is the periodic, this QT is periodic, they are all the same, and it becomes steady state duty ratio. Okay. If dk is different from dt, like this area, there will be some error which is shaded in brown color here. This is error. But error will be small if the variation of this duty ratio is very small. Okay, then this height, the height of the lamp will be lower than this, much lower than this. Then the error will be reduced. Okay, so that is ideal. So with this assumption, you are using dt as the continuous variable, and dt is in exact sense as the moving average of the QT over one switching period, and more precise definition of this is moving average of a switching function QT, and we perform the moving average with the sliding, while sliding the window of one switching period. Okay, so suppose we have this showdown, then this is the fixed, and we are moving this in this direction, and we are performing this averaging function. Then you will get this something like this, because duty ratio here is relatively large and small, and you will see this continuous signal in distance. But if you approach closer to this, or you magnify this area, you will see this kind of step. Okay, this part is the lamp part of previous signal. This one, this black line appearing something like this. Okay. Okay, so this is the old one. This is a new lecture slide. So we have this equation. You are using this equation. Oh, where is it? This equation. Okay. We want to justify this, or we want to understand this using the actual waveforms of buck converter. So here is a buck converter. Here is a buck converter waveform is this. Okay. First, forget about this part. Okay. This blue line is not there. Then VAP is DC VS. Average value of this is VS. Okay. And this is IC. This which is the same as the inductor current IL. Then average value of this is IL, which is constant. So this is obvious true, and this VCP is copy of this part during when this is connected to here. So during on time period, this is copy of this, and again this is a copy of this, and in between is 0. Okay, this is very obvious. Okay, very easy to see. So then average value of this is DTS. Okay, D can be varied, but still this relationship holds. Okay, and again here, so this is the inductor current IC, and this blue part this part moves to here, this part moves to here. Okay, let me clarify that with this. Okay, all right. So it's going down like this. This part is, okay, it's not aligned somehow. Okay, should be aligned vertically. Then this part is shifted to here, and this part is shifted to here. Okay, then this is the same, so you cut this and move to here, then you have this. This is IL. This is the DC value of this one, which is the average value of the IL, and this the average value of this one. This is IA, is DIA. Okay, so we have the average equation VAP. Average value of this and average value of this is VS and IL. This is obvious. Okay. Then average value of this. This is DVS. This is DIL, which is obvious. Then you replace this VS with this one. Replace this IL with this one, and you have this average equation. Okay. So this is so easy to see. So simple to see, but not so simple to swallow and digest. Okay? I spent some time to make this example. This looks obvious. It's like saying apple on apple is on apple. Okay? But there are something. Okay? Some complicated circuit. This relationship such a hold, then you can exploit this fact. Okay? Without much thought, without much thinking, you can guarantee this is true for any complicated situation. Okay, so let me show some examples of the further meaning of averaged model. So you have, this is the same buck converter, and this is the switched model. In here, this is the switch, and everything is periodic in here, and the switch drive signal QT is modulated in this fashion. Okay, you perform that moving average type things QDT, then looks like this sinusoidal fashion. That means the duty ratio is something similar to this. Okay, with this switch model is generating this. There is a ripple, triangular ripple, and this is average model. Average model is just has the same structure, but this PWM switch is replaced with average model of PWM switch, which has the shape of ideal transformer, but this DT is something here. So this is related with this one by this integration. And the integration is performed by looking back, okay, at the end of switching period. Okay, I explained that later on the previous lecture slide in great detail. So actually I generate this signal using this. Right? So it can be converted to this one if the PWM is implemented using this signal. Okay, so first generate this, and averaging this is very tough, all right? First generate this and use some PWM scheme and generate this. It will be much easier. They are same thing, okay? So I have this simulation result, and it exactly follows the moving average of this ILT of this switch model. This is one example, and this part is also important. So DT has this. DT is this kind of, this is the mathematical operation, and this is the simulation using the PSIM. All right. So I have two models. So you have this, right? I uploaded all the PC models. If you have time, you just use this. You modify something, or you repeat this as the means of to have concrete understanding about this. Okay, so this is power stage, and this is a PWM block, and this is this summation, and this is DC, and this is the height of the lamp. Okay, then PWM gain is just 1, so this becomes DC duty ratio, and I include this some sinusoidal wave. Okay, so this is the perturbation in duty ratio. Okay, but in time domain model, no, this in the switch model, there is no concept of continuous duty ratio. Instead of that, we have the definition of the V con is just the control voltage, and the control voltage is DC component is coming here, and AC component is coming here. They are combined together. Okay, so this is the V con waveform. So actually V con waveform is sum of this one and this one, and this 0.25 is here, and we have AC component. Magnitude of AC component is 0.06, is much smaller than this. 10 times, no, less than 10 times. Much smaller than this anyway. Okay, all right. So this is actually this is the control voltage, but it can be used as the duty ratio perturbation. And if I used this to generate this, okay. So if you perform the PWM scheme using this kind of lamp with lamp height of the 1 volt, then you will have this. Okay? So you have this, and you generate the PWM for the switch model, which is this. They're same thing. Okay. In here, this is in this switch model, this is used as the control voltage, but in this average model, this can be used as, so this one here, let me write down here, this one here. Okay, so this is, previously it was V con, control voltage becomes DT. All right, so DT. Okay, and this is, it was V con, but it becomes DT. You can use the same variable here as the control voltage, here as the duty ratio. So this is ideal transformer. So this is the V con is coming here. So this becomes DT, okay, which has DC value and AC value all together. So this is the model for the ideal transformer. In PCM, there is no ideal transformer, so I use this using this voltage source and current source, and I sense this current to emulate the function of ideal transformer. So this is the ideal transformer with the turns ratio of the DT, which is D plus DT hat, is same as V con in here. And the V con is also DC plus AC component in the previous simulation. Okay, so this is okay. Okay, you don't have to generate this first, and somehow you derive this. You can do it opposite way, which is much easier than the previous direction. Okay. Let me go 2 more lecture slide, and we take break. All right. So step input response of switch model and average model. So now you know this. This is the response of switch model with this step. So Vs was constant here, and I use the same input voltage waveforms like this solid line. Okay, then it generated this, and this is exact copy of this in terms of its average value. Okay, but assume you have this some sinusoidal component at high frequency. Still, this might be true because This is original waveforms. If you take average value of this becomes this one, and this one. Okay? So, all right. So this is one example. So in the past, the average model was used for the time domain simulation to get the average dynamic response of many converters connected all together, because in the past, simulating this switching circuit was not that easy job. Okay? For example, PSpice was not simulate the simple buck converter, closed loop buck converter switching on the principle of PWM. Okay? Was not easy. They think usually it's not possible to simulate that. But some guy wrote down very simple code, and I took his code. Okay, he's the guy is in some company. Company name is Unitrode. Okay, that is the chip maker, PWM chip maker. I forgot his name. His name was some strange name. Okay, so with that I was able to simulate this closed loop converter using PSpice. That was the kind of the challenging job there. So people use this average model to simulate the complicated system consists of many converters, and I performed one job, simulation of those type of converter that was sponsored by IBM company, and they are making the new mainframe computer, and the power supply guys there sponsored us to simulate that. So I used average model, developed average model. Otherwise, it takes so long simulation time at that time in the past. Okay. But now this simulation is just a piece of cake for all the students, because so many strong simulator. Some maybe the lousy one is PC, and the high end is something else. LT Spice is the free Spice version. Okay, it is modified for the power electronics people. So there is the best software for the power electronics, and Simplest is also good one. There are many. Even you can simulate this switching function using the spreadsheet like Excel. Okay, is not difficult now. So lot of this thing is gone, and another use of this is it can be used the DC analysis. You have average model of power stage or converter. Then consider this inductor is shorted and capacitor is opened, and every waveform is just DC component, average value of like this. Then the DC analysis can be easily done. Okay, I'll show one example. So those are two applications of this average model. But most important application or use of average model, the critical use is this one. You can linearize this average model because it is non-linear model, because this dt is time-varying function and this everything is time-varying function. So you should multiply two time-varying function, then that operation is classified as a non-linear operation. So you should linearize this to obtain small signal model which accommodate all the techniques you learned for the linear time invariant system. All the techniques you learned in the undergrad student or some graduate undergrad course and some graduate courses, they are assuming everything is linear time invariant system. Okay, for that this step is required, and this is the best use of this small signal model. Let me show one simulation example further, and we take a break and we come back after 2 minutes to finish up the remaining part of this lecture. All right, this is another example. In here, this is fixed by 0.5. I'm assuming this is open operation, so D is not perturbed. Only this one is changed, step changed. Okay, I didn't show this. This is a step change, right? So due to the some step change, and this black one is this switch model. It's not average model is here. Switch model, average model. Okay, this PC model has two things in one window. So this part is switch model. This part is average model. This is the response of switch model. And this green is this blue is this green, right? Greenish blue is the response of average model, and this black one is the switch model. Okay, so this is one example of using the average model. Okay, so average model is basically non-linear, so you can use for the very large disturbance, large state change. There is no limitation because the average model is a non-linear model. Okay, all right. Later on, you will see the small signal model. Small signal model can be used for the time domain response in limited range. Okay, all right. We take 2-minute break and come back to finish up the remaining part of this topic. Okay. This is the second part of this lecture. This lecture slide shows the extension of the small signal model, average model of Buck converter into other topologies. So this is Buck converter, and the small signal model average model was just replace this with this average model of PWM switch, which has the shape of ideal transformer. So you repeat these things. A is here, P is here. Okay, A is here, P is here. For the boost converter, A is here, and P is this side, C is here. Okay, you just rotate this. Then this is the average model of boost converter, and this is the average model of buck boost converter. Okay. Just take out this, and we derive the average model of this, and the pin-to-pin replacement of this with this average model of PWM switch will provide the average model of the converter. This is the open loop. Closed loop is the same. It remains the same. But you need to have the average model of everything, modulator and everything. Okay, with that you can simulate the average response of converter, closed loop converter using complete average model of converter. Okay, that was a very popular topic in the past, but we don't need that, right? Because there are so powerful simulator, just simulate it. Okay, so we don't need that, but this is very important to derive the small intermediate step to derive the average model of all the converter. If you take a look at this DT and inductor, they are coming together. Okay, you have DT, then L is here. You have DT, L is here. Okay, if you put one DT here, you are wrong. Okay, they come together. They come together because of the structure of this converter. It's not a rule or anything. It comes from the inherent structure of three basic converters and inherent structure of derivation of three basic converters. Okay. Last example, as the last example, let me show this. Okay. This is buck converter. Boost converter. You know the voltage gain of boost converter is this one. This is the voltage gain. Is 1 divided by 1 minus D. When D approach infinity, the voltage gain becomes infinity, which is nonsense. Okay. You can figure out what that is nonsense. Okay. Output voltage should be 0. D equals 1 means this switch is connected all the time. Then this is turned off. Then suppose there is some voltage will be discharged here. So eventually this voltage should be the 0, okay, not infinity, right? So there is some some singularity in here. Okay. So to solve that, then you need include this one. Okay. So you have ESR of this inductor, then everything becomes clear, right? Then this is average model of this, right? This is average model. So you replace this with this, right? This is the DC model. Assume this is shorted, this is opened, then you have this. Then to solve this equation, replace this ideal voltage source with this current source and the voltage source. Okay. You do this the other way around, but this is the most convenient. And the dots are here, and this voltage is Vs, Vo plus minus. Then this voltage is D was this side, so dVo in this polarity, right? Because this Vo is plus minus here, then dVo is this here, right? Because of this dot convention, right? And the current waveforms, this IL is coming in, then you have turns ratio of the D to 1, then DIL must come out from dotted terminal. So this is correct. IL is coming in, then DIL is coming out. Then this current is 1 minus the IL due to the KCL. Okay. Elementary circuit analysis. Okay, this is true. Then apply this to evaluate this. So there is a loop. Okay. So you apply KVL along this loop. Then this voltage Vs minus this one plus this one and minus plus this one minus this one, because polarity is opposite. So you should add this and you should subtract this, which is this, and divide that voltage by RL will give you IL expression. And VO this is IL lossing into the R. This times R is our voltage, and you combine together to obtain this. Alright? So then you rearrange this in this manner. This is the voltage gain of ideal boost converter, and you have some correction factor like this. If RL is 0, then this term becomes 1. So you come back to the ideal case. Otherwise, they are different. It has very strong effect on this voltage gain. So practical one, this is ideal one, RL is 0, and this practical one, RL is not 0. Then actual voltage gain comes like this. You have some huge deviation, and it converges, it is homing to this point, 0 point, not infinity point. Okay, that can be seen from this equation. Suppose D is approaching to 1, then this becomes 0, right? This becomes 0, and it becomes 0. It goes to the upstairs. Then when D goes to 1, this one becomes, in the downstairs there is 1 0. In upstairs there are 2 zeros, 0 squared. Okay, so 0 cancel, and this is 0, right? So this numerator dominate, so the gain is 0. So our voltage converges to this. Okay, so this is one example of average model to obtain the voltage gain of some tricky situation. This is one simple example. And in the last sometime 1 year ago, I lectured this boost converter. At that time, we used this m-second balance condition on capacitor and volt-second balance condition on inductor with 2 equations. We simultaneously solved that equation to obtain same result. But this one it provides some aspect of property of average model.